Hello everyone, my name is Austin Rovinsky, and I'm an assistant professor at New York University. This is the 11th lecture in my mini course on physical design databases, and this lecture will introduce you to SWIG interfaces. Now that you've created your own OpenRoad tool, you've seen how you can create C++ code to interact with OpenDB and potentially other OpenRoad tools. While this code is great for performance, it is not very user-friendly and not good for productivity. Every time that you want to make a change to your tool, or change the way that it runs, you would need to recompile the program to integrate those changes. One option to simplify things would be to create a runtime interface for users to specify commands. Imagine using cin, or reading from a text file, when the program runs so that you don't have to recompile. You can instead just adapt to the user input and perform the commands at runtime. If you start doing this, however, it turns into a slippery slope of how do you format the input? What syntax does the user have to follow? How much do they have to learn in order to use these commands? Things can start getting very complicated very quickly for complex software like OpenRoad. Instead, another option is to embed the interface in a scripting language like Tcl or Python. By creating an interface at a high-level language that users already understand, or at least that they can find many online resources to learn from, this greatly simplifies the learning curve for the interface and makes it very verbose by allowing users to use commands and language features alongside the embedded interface that they're already familiar with. In OpenRoad, this interface is done through SWIG. SWIG stands for Simplified Wrapper and Interface Generator, and it's an open source software development tool. SWIG automates the process of connecting C and C++ programs to a variety of high-level programming languages. You can find out more about the background of SWIG and its features by visiting the website. So how does SWIG work? As a simple example, let's create a sample C++, or C rather, file, which will be swigged into a higher level language. Here we have three functions. We have fact, we have mymod, and then we also have getTime here. Fact you may recognize as a recursive function in order to calculate the factorial of a number. Mymod returns the modulus of a number, and then getTime returns the current time as a string. Next, let's create the interface file. Typically, these interface files are created with the .i suffix, and these are sort of the magic that makes SWIG work. The interface files share very similar syntax to C, and you can look up way more on the syntax by going to the SWIG website, or by looking through some of the .i files in the OpenRoad repository for examples. This interface file will typically be used to create Tcl modules, and at least in OpenRoad, which can be loaded using a Tcl shell or through the OpenRoad is built-in Tcl shell. For the first part, on the left, you can see that there's this module, a syntax, and then there is a list of function declarations here. And these can either be function declarations, or more commonly, for larger projects, you can include header files here. And the point of this part of the program is to essentially declare all of your functions to SWIG so that it knows what is the total space of available functions that it has. Then on the right here, we have the actual declarations, or rather instantiations of all of these functions. And these are essentially saying, of the ones that were previously declared, which ones you actually want to create a wrapper, an interface wrapper for using SWIG. And so these are the ones here that will be, in this case, exposed to Tcl or whichever the other higher level language that you're targeting. You can also see here that in the previous example we had, or the previous slide, we had the variable, the global variable called myVariable, and that's being exposed here as well. So last, we just need to invoke SWIG to create the interface. You can see that there is the -tickle flag used when running the SWIG command, and then it's run on the example.i interface file. And then the next step is to take this example wrap.c file, which is generated from SWIG. So it takes this example.c file, and then it creates a wrapper C file, and then compile them together using your favorite compiler, in this case GCC. So once that creates an output file, and then in this case this is just creating the final example.so, which is the shared object file, which contains the binaries of the functions from the .c file. Then you can actually open up a tickle shell here, and then load your shared object file, this example.so, and the module name, example. And then once that's done, all of the interfaces that were exposed using the interface file can now be run inside of your tickle shell. So as a quick example, you can print the string or print whatever the contents of my variable are, and in this case it's a double, 3. You can also run factorial as a function, the fact, with 5 as the input, and then you'll get the correct output. You'll get my-mod 7 and 3, correctly prints 1, and then getTime, which also prints the string. So for all of these functions, essentially what's happening under the hood is your tickle code is doing a call out to the shared object file, which runs in binary format your C code under the hood, and then it returns the result back to the shell. So through this whole process, you were able to write some C code, turn that into a binary, and then execute that code using shell, using a tickle shell or any other higher level language to make things a lot more convenient. And you can use the results that return from these commands in any way that you want. In this case, they're stored just like any other normal tickle variable. So you could store these results to a variable. You could use them in if statements. You could print them out. You could do anything you could do in a normal scripting language with them. So in OpenRoad specifically, SWIG connects to OpenRoad C++ to both, or connects OpenRoad C++ to both Tickle and Python interfaces. Currently, Tickle has the best support, and it's designed to be the primary user interface. It should be noted that not every C++ command from OpenRoad is exposed to the end user through either Tickle or Python. Firstly, only commands in the interface files are exposed, and these are limited to commands that just the developers define, or also commands from the database, particularly OpenDB's db.h header file that we've discussed previously. Second, not every Tickle command is meant to be exposed to the user. OpenRoad uses a paradigm of wrapping C++ commands with Tickle commands in order to do error checking in Tickle and other functions before passing that command onto the C++ code. Here's an example of this in action from DPL, which is the detailed placer tool in OpenRoad. This code has the main header file of opendp.h, and you can see in here that there's this class OpenDP, and we can have some public member functions, private member functions, many more things which are not mentioned here just for brevity. And we can see that there's 3 functions, for example, that are public. We have this legal cell pause, we have check placement, and then we have set padding global. And then we also have several private functions, but we can tell right away that because these functions were declared private, that we don't want to be exposing those to the user. So now if we look at the opendp.i interface file, so this is the file that was created specifically to expose certain interfaces, then we can see that there's this check placement command, and there's also a set padding global command, And these are, of course, just not the entire file. These are just a small subset. But we can see that there's a couple things right away. One, we can see that there's this namespace DPL, which kind of wraps all of the rest of this. And that's important because this will create a namespace in Tcl, which we'll see how that works on the next slide. And second, this also has different command names here. So we have check placement over here, and that's in camel case, and then we have check placement CMD, short for command, here in the interface file in snake case. So essentially two different functions, but you can see in here that this is essentially calling OpenDP, the check placement function here, and passing things along. So that's what the interface file looks like, at least for these couple of commands. And we can also see that not every function that's public has to be exposed. So this legal cell pause, we can see a comment right here, call from RSZ. So this one is mainly intended to be called from a different function, a different tool within OpenRoad. Does not necessarily need to be exposed to the user through the interface file. And so now if we look at the interface file versus this opendp.tcl, which is actually a Tcl file directly in the source code of OpenRoad. This is, a scripting file, and the point of this is that when you compile OpenRoad, this Tcl code actually gets directly embedded into the application. And so it exposes this sort of Tcl interface that's provided by this file. And so if we look at what's actually being used over here, we can see that there's this Tcl proc, which is, you can think of it like a function in any other high-level language. There's arguments that are supplied. And then there's actually some error checking that goes on here. So there's a check here to make sure that there's a design loaded, otherwise it will return an error saying that there's no design block loaded. It does some checking on the arguments to make sure that either they exist and variables are set correctly. And then finally at the bottom here, this is where we have our check placement, and then it supplies the arguments that correspond to the arguments seen over here in the interface file. And here's importantly where the namespace comes in. So we can see that in order to call this check placement, it has to be called with the DPL namespace. If you were to just try to run check placement, you'd probably, or check placement CMD rather, you get probably an error saying that it's not found. So you need to make sure that things are in the namespace here. More thing to note is that the reason why things are hidden sort of from the global namespace and why we have this check placement command which wraps this other command, even though technically you can access this check placement command, it's not essentially designed to be the top level user interface. This check placement Tcl proc is designed to be the one that's called, the one that will show up in documentation, because it has all this error checking around it, things that make a nice user interface. Versus down here, the DPL check placement command is just passing it directly to the C++, where there isn't error handling done. If you pass improper commands that way and you kind of work around the error checking, then you could end up with your program crashing, segfaulting, other miscellaneous problems. And then one other thing to point out is that also there is no set padding global equivalent command here. So you can have things that are exposed in the Tcl, in the interface file, which do become Tcl procs, or things that you can call from Tcl, but they don't necessarily need to be exposed to the user. So this set padding global function is actually only used within other functions as a helper function. So that wraps up everything for this lecture. I'd like to take a moment to thank NordTech, who provided the funding to make this mini course possible, and thank you for taking the time to watch it. I'll see you next time.